Hello and welcome to Living Proof, the Isaac Newton Institute podcast. My name is Dan Aspel. In this episode, we'll be catching up with Tomer Schlank and Jeremy Hahn, who at a recent I&I workshop made a very significant announcement regarding Ravenel's telescope conjecture in the field of homotopy theory. We hope you enjoy the episode. Welcome to the latest episode of Living Proof, and today joining me on the host side of the podcast is Marianne Freiberger.
Hello.
And we are joined in terms of guests for today by Jeremy Hahn.
Hello.
And Tomer Schlank.
Hi.
Now, the reason, as we will have put in the show description, that we're speaking to you is because you guys made a very significant announcement within the past month about the telescope conjecture. You specifically, you disproved it or part of it. I'm going to let you guys tell us more about that. Now, our listenership is a very broad mathematical audience, and I realize that this is a very complex problem to describe, but we would love to hear from you the best description you can give to us about the problem that a general audience might be able to understand. But I'll hand over to Marianne, who has some thoughts about this.
Let me just, before we talk about the map, emphasize that this is a joint work with Ishan, Levy, and Robert Burklund.
Fantastic. Well, yeah, absolutely important to credit everyone that's involved in this at all, and we will make sure we put that in the description as well. So you two are spokespeople, effectively, for the team that has handled this. So, Marianne, would you like to sort of use your questioning to break into this issue, perhaps?
Yes, so I've read up on the topic a little, but I'm absolutely no expert in it. So it's my first kind of encounter with it. So I was thinking the telescope conjecture, it does fall broadly into the field of homotopy theory. So to give people who haven't come across this a bit of a handle on what that is and why it can tell you interesting things, I was thinking we could start by thinking about drawing loops, right? We can draw loops on a sphere, or we could draw loops on a torus, which is a donut, and that can actually tell us something about those shapes. Can you expand on that, please?
Sure. So, yeah, we're interested in understanding shapes of, and for us in math, a shape doesn't have to be something that you can have inside three-dimensional space. It can be something that you can also see in very high dimensions, and there's different approaches to how to study shapes, and kind of very broadly, geometry studies shapes by thinking about quantitative measurements like volume or distance, but topology studies more qualitative properties that we say the properties of shape that don't change if they're all made of rubber, so you can twist them and flex them. And when you do that, what you realize that essentially the main properties that are still describe your shape best are the holes that you have in it. So how do you understand holes? And the idea is that the way to understand the hole is to say, let's say a one-dimensional hole is if you can draw a loop that you can contract. So, for example, like in the example you gave, in a torus, there's a one-dimensional hole because you can draw a loop around the torus, which cannot be contracted. And we say that a two-dimensional sphere don't have any one-dimensional holes because every time you try to draw a loop, you can contract it. But a two-dimensional sphere does have two-dimensional holes. Because the sphere itself can put a two-dimensional balloon that cannot be contracted, and that's the sphere itself. And it's not immediately obvious, but it's not that hard to prove that for the torus, for example, although you have one-dimensional holes, you don't have two-dimensional holes. And this idea of considering holes in higher dimensional shapes, which are spheres that you can map in without contracting, or even saying that's a way we understand holes in higher dimension, and you can ask something slightly more refined than just can I put in a sphere that cannot be contracted, you can ask yourself, well, saying that a sphere can be contracted is the same as saying that you have a continuous family of spheres that goes all the way to the point. So more generally, you can ask, given a shape, about all possible maps from, let's say, a sphere of dimension 7 up to an equivalence relation. You think about those two such maps as the same if you can move from one to the other continuously. And those are called homotopy classes of maps. And the collection of such equivalence classes is called the homotopy group. It's called the homotopy group because it has a natural structure of a group. Yeah.
So just to slightly, yes?
Yeah.
Yeah, just to slightly backtrack. So what we had here, like we started with loops. Loops are really just a function or a map from a circle into the space that you're looking at. And then you're saying you can also look at maps from higher dimensional spheres. So a circle is a one-dimensional sphere. The ordinary sphere is the two-dimensional spheres. But we have higher dimensional spheres. We can look at maps from those higher dimensional spheres into the space, the topological space that you're interested in describing, because that characterizes that space. That gives us some idea about what that space is like, right?
That's exactly right.
Right. And in homotopy theory, we're interested in studying those continuous functions in from higher dimensional spheres up to continuous deformation, which is what a homotopy is.
Right. So because we're thinking about loops or spheres that can be contracted, that corresponds to functions that are homotopic to each other, and they form classes.
Yeah, so a loop can be contracted if it's homotopic to just the constant loop that is all a function that lands only at one point.
Yeah, right. So then from the sense that I got when I was reading up about it is that, so at least when it comes, if you're looking at maps from a sphere into another sphere, potentially also for other spaces, there is an interesting result by Freudenthal, I think, which says that these homotopy groups, if the relation between the two spaces is just right, they're all isomorphic. There will be chains of isomorphic homotopy groups, which means that essentially these groups are the same. Is that right?
Yeah, this is called stabilization. So, so the first thing I think maybe it's worth emphasizing that there's something which is kind of surprising and was actually not expected when this notion of homotopy group originally was defined, which is that if you use this method of measuring holes, of considering maps from spheres up to contraction, you have high dimensional holes inside low dimensional spheres. So what I mean by that is that you can write down, for example, an example of that is that you can write down a continuous map from a three-dimensional sphere to a two-dimensional sphere that cannot be contracted, that cannot be deformed into a point. So understanding the general question about what are the homotopy classes of maps between spheres of different dimensions, that became, it's still one of the most important questions in the field in homotopy theory. And Freudenthal theorem that you mentioned tells us something about the relationship of those maps when we vary the dimension. Specifically, if you have a map from an n-dimensional sphere to a k-dimensional sphere, it's possible to apply to do a construction called suspension to get a new map now from an n+1 dimensional sphere to a k+1 dimensional sphere. So it increased both dimension plus one by one. So this gives us a map from the collection of all homotopy classes of maps from n to k to all homotopy classes of maps from n+1 to k+1. And what Freudental's theorem tells us that if you do this again and again, at some point, that doesn't change anymore. It stabilizes. So this means that if you're interested in maps in the collection of maps between two spheres, such that the difference of dimension is, let's say, 10, and the sphere that you map into is of high enough dimension, it doesn't matter what this dimension is. So we can we can try to solve something that would be an easier problem first, which is to study the stable homotopy group of spheres. And that's a collection of groups, of abelian groups, that depends only on the difference between the two dimensions. So there's one for every integer.
Mm-hmm. So then the task becomes to understand this landscape of stable homotopy groups. And the result that you have disproved is called the telescope conjecture. And is it right that the telescope conjecture would have given us a method for understanding this landscape, and you've now proved that this method does not work?
I think that is fair to say. And not only sort of did we prove that it doesn't work, but one consequence of what we do is that it fails drastically, and this landscape is much more complicated than predicted, maybe by Ravenel when he predicted this telescope conjecture.
Oh dear. So is everything lost? Do we have to go back to square one, or did your work and the work of your collaborators give insight that would help with other approaches to understand that stable homotopy landscape?
Well, it gives us positive information. So one of the things that, you're looking at this sequence of abelian groups, and the first one of them, the 0th one, is the integers, but all the rest are finite abelian groups. So what we're looking at is, if you want just a sequence of either, you can think about finite abelian groups or just their orders, which are just a sequence of integers. And if you look at this, table, and you can find the first few sizes appear on Wikipedia, and there's, if you look at there are still papers published in which people push the knowledge higher and higher, say, okay, we computed everything up to 60, we computed everything up to 80, etc., etc. But it seems very random somehow. So what the work that by many people that one kind of a keystone of it is Ravenel's conjecture, and he had more than one conjecture. The telescope was just one of them, and all the rest were actually proved, not disproved. Suggested certain patterns that explains this sequence that seems apparently random. And essentially explain that those, if you can break this pattern into certain wavelengths and see periodic phenomena appearing in them. So that was, and those periods are there, but they appear in a more complex way than let's say the most optimistic possible hope, which was the telescope conjecture. But nevertheless, the way that the way we disprove it does give us positive information. It tells us, for example, it gives us a lower bound on how large those groups are. So we now know that their size have to grow at least as fast as something.
Right. So you have some information. Now, I think that when you announced this result a couple of weeks back, that the person who made the conjecture and some more conjectures, Doug Ravenel, that he was there in the audience. Is that right? How did that feel to announce it when the very person who's made the conjecture was there?
Well, I think that was a special moment for all of us. And so he was there, and also Mike Hopkins, who had proved most of them along with his collaborators, except for the telescope conjecture, was there. So in the room was sort of the whole history of people who had interacted with these conjectures. And this was a good time to announce it. And we really appreciate the conference that was at the Newton Institute that was put on, that brought all these people who had interacted with the conjectures together, and seemed like the perfect time to explain our work.
This conference was also honoring, in fact, Mike Hopkins, and we felt that that's very fitting. He's a great influence in the entire field of homotopy theory, and would definitely a great influence on all of us in our work. So
it's interesting to note that this event that we're talking about was, I think it was called a panorama of homotopy theory. And it was a satellite event, so it didn't take place here in Cambridge, but it was at the Mathematical Institute in Oxford. And that itself, as you've suggested, was a follow-on from a 2018 programme, which did take place here in Cambridge, called Homotopy Harnessing Higher Structures, which has got a lot of H's in it, so I tripped over that slightly. What you've just described there about having these significant figures and a wonderful atmosphere, I mean, it seems like a really rich field, and I'd love to hear how the two of you came to it and why you came to it. What attracted you to this particular part of mathematics?
Yeah, well, if we do it chronologically, then I should go first. So, I did my PhD at the Hebrew University in Jerusalem, and I was studying a different field of math called the Diophantine equations, which is a part of number theory. And I was, if you have an equation and you want to show that it has a solution, well, one thing you can just show is you can just show the solution. You can just write it down. But if you have some kind of an equation and you want to show that it can't have any solutions, that's much harder because there's a priori infinitely many. If we're going back to the history of the Newton Institute, very famous this Diophantine problem is the Fermat-Last theorem, and whose proof was announced at the Newton Institute. And that's exactly this kind of problem in which you have an equation and you want to show there's no solutions. How do you do that? So anyway, I was studying these kind of things, not something as sophisticated as the Fermat-Last theorem, but the Diophantine equation as a PhD student. And I had my roommate at the time was someone who did homotopy theory, and one day he looked at the methods I was working on, just the thing that I wrote on my page while trying to find ways to show that there can't be any solutions, and he said, "Hey, this looks like homotopy theory. Why are you doing homotopy theory?" And I said, "Well, I don't really know a lot about that. Can you tell me?" And what happened was that it turns out that it really was. So I came to homotopy theory from number theory, and I had a chance to do my postdoc here at MIT, where I'm visiting right now as well. And I came to know, via this initial work on homotopy theory that I did, I came to know the community of homotopy theory here. And, the community, the mathematical community of homotopy theory is really amazing. It's just, really, I think, one of the warmest, kindness and full of humor and support scientific communities I have ever interacted with. And I just, and the subject itself is just amazingly beautiful. So I got more and more involved with it while I was here at MIT. Jeremy was there, I think, an undergrad.
Yeah.
So we,
Yeah. So, as Tomer said, one thing that's very attractive about homotopy theory is that it's so connected to so many other areas of math. So these homotopy groups that we now know are even more rich and complicated than the telescope conjecture predicted. They're connected to differential topology, they're connected to Diophantine equations. And so I think that's one thing that really attracts me to the subject is all of the central connections it has with other areas. And, I was an undergrad at MIT, and MIT has been for decades a real center for homotopy theory. And I was attracted by a lot of people here to go into that, including Tomer, who was a postdoc here when I was an undergrad, first getting into some of this stuff.
It sounds like there's a lot of possibility here as well, because I can see from the expression on your faces how exciting this last month has been, being part of that community and announcing this great announcement that you were able to make. It sounds like there's a lot lying ahead of you. Is that fair to say?
saying that two things are not, so the telescope conjecture, we haven't said what it is formally, but kind of, let me just say in a very, very vague way, is that the telescope conjecture predicts that two things are the same. And what we did is show that they're not the same. And saying the two things are not the same is a very, there's a lot to be left to do if you do know the two things are not the same, right? Measuring their difference, how many things are in the middle, we know that, I can say a little bit more. We know that one of them is small and the other one is large, but how much larger and what's in the middle, and so there's really, really, we have this thing that definitely opens way more questions than it answers, and we already have a follow-up work planned, which is also the four of us, and also joined with the Shahar Carmeli and the Orionovsky. That's already a follow-up work prepared, but there's so many other questions and so many other directions to go that it's very exciting.
Yeah, I mean, I'm very hopeful that the techniques here will continue to yield new results and more refined information. And I would say also that, there's a lot going on in homotopy theory in general, not just from us. There's so many new techniques and results right now, which is part of why we were able to do this after it had sat around for decades previously. And so it's an exciting time to be in homotopy theory.
Brilliant. And I'm not sure if Marianne has any other sort of parting questions, but one I would like to ask is, how easy is this kind of collaborative work? Would it be easier pursuing something yourselves? Do you tend to combine really well in the way that you research? You don't tread on each other's toes at all, I guess is what I'm asking. Does it all work well, heading in the same direction?
I find it a delight and a privilege to work with Jeremy and to work with Robert and Ishan. It's just wonderful. It's a lot of fun, and I think one thing that maybe more generally that people sometimes, beside of our specific collaboration, that people have maybe a misconception about math is, I think that mathematicians are usually very social creatures, and a lot of research is done collaboratively, and that's a big part of the fun and a big part of where the inspiration comes from.
I would say specifically for this project with Robert, Tomer, Ishan, and I, we all brought previous results and previous intuitions that were absolutely essential. And our argument here actually has a lot of moving pieces that no one of us could have really put together.
Oh, that's a great answer. Thank you very much for it. So, Marianne, was there anything else you wanted to ask before we let these guys get back to a full day of work at MIT?
I think we can let them get back to a full day of work so we find out more about homotopy groups.
Wonderful. Well, thank you both very much for joining us. It's been such a pleasure.
Thank you very much.
Thank you.
Cool.
Thank you.